You may have seen in the previous videos when we solved linear programming problems by graphing, the problems tended to get more complicated as we introduced more and more problem constraints, that is, more and more inequalities. And also, if we tried to graph a system that had more than two variables, instead of x1, x2, maybe it has x1, x2, x3, x4. We can't do that because we can only graph in two dimensions. Realistically, I mean, you can try to graph a three-dimensional problem, but it's very difficult. So what we need to do is find an algebraic approach rather than a graphing approach to solving these linear programming problems. And it turns out there's methods to do this. And so one method that we're going to talk about here is the simplex method. And this method is used when you're maximizing a problem and all the constraints are in the less than or equal to form. Now, there's two other methods. There's the dual method, and the dual method is for when you're minimizing a problem and all the constraints are greater than form. And then the big M method is actually used if you have mixed constraints where you have less than equal to, greater than equal to, or even some equal to constraints. So we're going to start with the first one here, the simplex method. So the first thing you need to know about the simplex method is that it can only be used on a special class of problems. So the simplex method will only be used for what I call standard maximization problems, and they must be written in standard form. Now, a standard maximization problem obviously must be a maximization problem, and all problem constraints must be written in the form less than or equal to a constant, and that constant must be non-negative. Now, it can be 0 or a positive number, but it can't be negative. And you also must have the non-negative constraints. The non-negative constraints must be included. So here are two problems that fit the form where we could solve using the simplex method. Notice this problem you're maximizing, and notice that you have less than or equal to constraints, and they're less than or equal to non-negative numbers. So 10 and 8 are both non-negative numbers. And then last, you do have your non-negative constraints here. Okay, and then here's another one. Notice here you're maximizing, and notice that less than or equal to 23, that's less than or equal to a non-negative number. Less than or equal to 8 is less than or equal to a non-negative number. And less than or equal to 7 is less than or equal to a non-negative number. So all three constraints satisfy the conditions, and we have our non-negative constraints. So on these two problems, we actually could use the simplex method to solve them. But on these other problems, they're actually not standard. This one's not a standard maximization problem because your constraint here is greater than instead of less than. This one's not standard, even though both constraints are in the less than form. This is a negative number, and remember the constraints must be less than or equal to a non-negative number. And then notice this one does not have the non-negative constraints, like we have up here, x1, x2, x3 is greater than or equal to 0. So none of these, these three all would not be in a standard maximization problem. Okay, so let's relate the simplex method to the graphing method here. Now, let's take this problem, p equals 50x1 plus 80x2, subject to these constraints. Now, earlier we solved this problem by graphing, and we saw that the corner points were 0, 0, 0, 16, 26, 28, 0, and that the optimal solution was a maximum of 1480 at x1 equal 20 and x2 equals 6. Okay, now I want to show you how this simplex method is going to relate to the graphing method. First of all, let's start with the definition of slack variable. A slack variable is a variable that is added to one side of a less than or equal inequality in order to make it into an equation. In other words, it takes up the slack. So for instance, I'm going to do kind of a silly example here. Let's say that we know that that my weight is greater than or equal to your weight. Or another way to say that is your weight is less than or equal to my weight. So if we know that your weight is less than or equal to my weight, well, if you weigh 150 and I weigh 250, then we would have to add 100 to take up the slack in your weight to make it equal my weight. If you weigh 130 and I weigh 200, the slack would be 70. Now, but if we both weigh 200, then the slack would be 0. So basically, we have to get your weight to equal my weight, we have to actually add some value, and we don't know what it is, so we'll just say it's some unknown value, S1, and S1 has to be a non-negative number. So again, up here I gave you some known values, but what if we don't know the values? What if all I know is that your weight is less than or equal to my weight? Then if I add S1 to your weight, that would make it equal my weight. So basically what I'm going to do here for this first inequality, I have x1 plus 2x2 is less than or equal to 32. So the left-hand side is kind of like your weight, and the right-hand side is kind of like my weight. So we're saying your weight is less than or equal to my weight. So to make your weight equal my weight, we add a slack variable to the left-hand side. So we'll add a slack variable to the left-hand side, and now that will convert that inequality to an equation. And also for the other one, we'll add a new slack variable for this one, for this less than inequality. Since this side is less than or equal to this side, we know there must be some number that I can add to the left-hand side to make it equal the right-hand side. And so now, when I put these two equations together, now I have a system of equations. But the problem with this system of equations is that I really have too many variables in this problem. So this is a dependent, that should say dependent, not independent. This is a dependent system of equations, and it has infinitely many solutions. So if you were to set two variables equal to 0, then we could actually get a unique solution. So let's do that. Let's set, since we have too many variables here, see, since we have two equations, we'd like to have two variables, but we actually have 1, 2, 3, 4 variables. So we could just call two of them non-basic variables, and non-basic variables will always equal 0, and then we can solve for the other two variables by letting two of these variables be 0. And then what that will give us is that will give us a basic solution. And sometimes a basic solution is feasible, and sometimes they're not feasible. And so the way you know a basic solution is feasible, as long as it doesn't have any negatives in the solution, it's feasible. If there's a negative solution, it's not feasible. So what I'm going to do is I'm going to show you every possible way to let two of these variables equal 0. In other words, I'm going to show you every possible way that we can let two variables be non-basic, and then we'll solve the system. Okay, so here's the system. Now, if I were to let x1 and x2 be non-basic, then that would just wipe these terms out, right? Because if they're non-basic, they would be 0, right? So if I let x1 and x2 be non-basic variables, then I could look at this and solve for S1 and get 32 for S1, and S2 is 84. So that would give me 3284. Now, the point that would correspond to on the graph would be the point 0, 0. And since these points are not negative and these values are not negative, then this is a feasible solution. Okay, now let's pick another pair to be let's say that we let x1 be 0 and s1 be 0. In other words, we'll let these two be non-basic. Well, if you let x1 be 0, that would eliminate these guys. And if you let s1 be 0, that would eliminate this guy here. And then you could take the first equation and solve for x2, and then that would give you 16. And then if you plugged x2 into this equation, you could actually plug x2 in here and get 64 plus S2 equals 84, and then you could easily solve that for S2, and you would find that S2 would have to be 20. So the X values here would be 0, 16, and the S values, S1 would be 0 and S2 would be 20, and since none of these are negative, that's a feasible solution. Now, what if we let X1 and S2, say we let X1 and S2 be non-basic. In other words, let those be 0. So that would wipe out X1 and it would wipe out S2. Okay, now if we solve this for X2, we would get 21, and then if you took the 21 and plugged it back into here, you would get 42 plus what number equals 32. So S1 would have to be a negative number. S1 would have to be negative 10. So you would get at 21 for X2, but you would get negative 10 for S1. So your points would be 0, 21, and the S value would be negative 10 and 0. S1 would be negative 10, S2 would be 0. Now this is not feasible because one of our variables are negative, so that's not a feasible solution. Alright, let's let X2 and S1 be 0. So again, I'm going to go through each one of these. So if they're 0, X2 and S1 is 0, okay, then I can see that X1 from here would be 32, and then if I plug 32 in here, I would get 96 plus some number equals 84. So that would, S2 would have to be negative 12 to make that true. So then for that solution, I would get X1 and X2 is 32 and 0. S1 and S2 would be 0, negative 12, and since a variable is negative, that would not be feasible. And then the last couple that I could do here is I could let X2 and S2 be 0, and so hopefully you're getting the hang of this now, what I'm doing. But if I let X2 and S2 be 0, then I would solve this equation for X1 and get 28. And then I plug the 28 back in here, and I could solve for S1 and get 4. So I would know X1's 28 and S1's 4. And then so that would give me 28, 0 for X1, X2, and 4 and 0 for S1, S2. So no negatives, so that would be feasible. And then finally, I could just let S1 and S2 be non-basic so that they disappear. And then the solution would just be the intersection of these two lines, which we know is the point 26 from working with these earlier. So X1 would be 20, X2 would be 6, and then S1, S2 would be 0, and that would give me 20 for X1, 6 for X2, and then 0 for S1 and S2, and that would be feasible. Now, I want you to notice something here. Notice that four of these points yielded feasible solutions. 0, 0 is a point on the graph, it's feasible. 0, 16 is a point on the graph, it's feasible. 28, 0 is feasible. 26 is feasible. Now, do you remember what those points were? Those points were the corner points. Though all those points were the corner points of this actual graph. Those were the 4 corner points. Now look at the non-feasible ones. The 0, 21, and the 32, 0. Well, that corresponds to the points outside the region. Like this point up here that's not in the region, that's 0, 21, and then 32, 0 was over here outside the region. So obviously they're not feasible because they're not actually in the region. Okay. So actually I summarized this here. I summarized this here for you. And so you can just pause the video and read this, but I do summarize that the feasible solutions are these 4 points that were the corner points. So obviously there is a relationship between the points on this graph and the equations that we were working with, and in the next video we're going to be off to learn the simplex method. So we'll actually learn the simplex method in the next video. This video was just to kind of set it up for you.